we'll see how that goes.
It should be fun.
Yeah? Good, thank you. Welcome to multi-level modeling for longitudinal data analysis, basics and applications, if you're so inclined. My name's Molly McGill. I'm here from the Center for Alcohol and Addiction Studies. I teach this seminar as part of a 2-week cycle, or a 2-year cycle. This year being multi-level modeling, and then next year we switch back to OLS regression and focus mainly on doing mediation and moderation in a regression framework. So can I just get first names and the type of longitudinal data you work with or hope to work with, or just what you're hoping to get out of the class? Start with you.
Hi, Jenny Pulowski. I do HIV research, so my dissertation actually looked at daily level relationships between food insecurity and medication adherence, so I have some kind of growth curve modeling experience, but I can always pick up more.
Okay, and do you have data that you think you might work with in the class, or like as we move along?
Yeah, so I have additional data that is also daily.
Okay, all right, great.
Nested within participants.
Okay. Hi.
I'm Jessica Albert. I do research on Alzheimer's and cognitive decline, so looking at what kind of things will predict future outcome longitudinally.
What kind of things?
What kind
Meaning
of
like
biomarkers, neuropsychological testing, things like that will predict future outcomes.
Functioning, essentially, over time. Okay. Hi.
Hi, I'm Ashley Clausen. I study child smoking and child secondhand smoke exposure and look at either changes in one or both of the processes.
Okay, so again, sort of survey type design. Okay, great, thank you. Hi.
I'm Leslie Brick. I have worked with some health behavior intervention data in schools, and right now I'm proposing to do some EMA data.
Okay, and EMA data with kind of what predicting what, generally?
It's going to be in looking at parents and adolescents following discharge from the hospital after a suicide attempt. So it's going to be looking at kind of their affect during that time.
Okay, great. All right. Hi.
I'm Shana Bassett. The main thing I'm working on right now is with Jane Metric. She's got longitudinal data kind of tracking the trajectory and returning veterans of the development of mental health issues, substance use disorders, survey data after returning from Iraq and Afghanistan.
And so over how much time?
A year.
Okay. All right, great.
I'm Molly, and I'm hoping to look at immune biomarkers as a function of alcohol use over time.
All right.
I'm Tim Janssen. I've mainly been looking at 4-year survey data, looking at like both latent growth curve modeling as well as survival modeling to model the outcome. And I'm gonna be doing EMA stuff, as you're aware. So hopefully that's what I'm hoping to take away from this, like how to effectively model both within and between level subjects.
Okay. And
effects.
I don't know if you said this, outcome of what type of outcome?
Substance use.
Substance use outcomes. Okay, of treatments?
No, in this case in adolescents, just levels.
Okay, got it. All right, thank you. Hi.
Angela DeBello, longitudinal data with college students after they've gone through an alcohol intervention and looking at changes in drinking and alcohol-related problems.
Okay. All right.
Hi. Carolyn Kirk. I have used a lot. I've used these models before, so I'm just excited to get to learn more. But longitudinal data in children with ASD.
ASD.
Autism spectrum disorder.
Okay. All right. Thank you.
Hi, I'm Marissa. I do health services research, typically looking at policy and organizational factors that impact a variety of health outcomes. So I tend to look at EMR data, electronic medical record data, and have used like multi-level modeling to do that.
Okay. So, and is your data in a longitudinal framework, or are you working with different types of nests, like hospitals? Or
Both.
Both?
Yeah.
So potentially 3-level models?
Potentially, yeah.
Okay. Okay. Hi.
Hi, I'm Diana. I'm a researcher.
What's your name? Sorry.
Diana.
Diana. Okay.
It's focused on early child development, looking at biopsychosocial models. So, and I've collected data from the classroom. So I've done more nesting, like in the 3 classrooms and that sort of thing. And then thinking about family level stress and how that impacts.
Okay, so families as nests, classrooms as nests. Adding longitudinal to that, or?
Potentially.
Okay, all right. Hi.
Hi, I'm Casey Claiborne. I mostly focus on HIV medication adherence and illicit drug use. So most of my data will be clinical trial data with longitudinal follow-ups.
All right, great. Hi.
Hi, I'm Carly Goldstein.
Is it Carly?
Carly, yeah.
Okay.
I do prevention, secondary prevention, and intervention for cardiovascular disease, and a lot of my work is multi-level modeling because I do medication adherence data over a long period of time.
Okay. And you said cardiovascular disease? Mm-hmm. Okay. All right. Thank you. Do you want to tell me your name and what type of longitudinal data you work with? And if you want, you can move in, but you don't have to.
I'll move in.
Okay.
Sorry, I don't want to.
Hi, I'm Murray. Some of the longitudinal data of its multi-level nested models, looking at
multi-level
nested models.
Okay.
One of the multi-level models I've worked with is looking at couples data.
Okay.
And through the course of psychotherapy, and so and another is through family dynamic. Over the course of time, this was like a 12-month intervention.
Okay. So couples, people nested within couples,
Yeah.
Potentially also within time. All right.
Hi, I'm Liz Aston. And I met Cass. I don't have multi-level data right now, but I want to be able to do it in the future. So.
Okay. Yeah. That's fair. What did I miss? You?
Me.
Okay.
Hi, I'm Marissa. I also am not working with multi-level data right now, but in the future, I like to work with a lot of data from schools. So.
Schools and.
So right now it's like kind of like school. I mean, there's a lot of different things, but I guess schools and reports of like connectivity over time and things like that. But I'm just starting to look at it.
Okay. All right. Thanks. Hi, Ethan.
Hi, Ethan Cass. I might be working with EMA data.
Okay, and EMA data, looking at what and what?
I don't have access to it yet, so I'm not quite sure.
Okay.
The most
what type of outcomes are you typically interested in?
Mostly substance use, craving in real life.
Okay.
And looking at maybe predictors of those.
Okay.
Yeah.
Who else?
So I'm Jess, and I've done some MLM with longitudinal substance use data and some daily diary data, and my work now looks at mechanisms in the development of BPD, and I'm hoping to get both some EMA data for that.
When you say mechanisms, you mean like predictors, or do you mean like mediators?
More of some of both, actually.
Okay.
So,
yeah. Hi.
Hi. I'm Kara. I'm from Cass. I have very little experience with MLM, but I'm working on a number of different projects with multiple assessments for longitudinal outcomes related to weight and cigarette smoking. So I'm not, all too familiar and just really interested in learning a little bit more for now.
Okay, good. Thank you, everyone. So we have like a rich diversity of topics as well as levels of experience, which is good. I do teach the class as a basic introductory class, but I think that I'm used to having a range of experience, so the folks who have more experience are able to bring in either their knowledge or their sort of other level of questions into the discussion, and it seems to work out just fine. So what I do is, as an analyst on projects, I work with clinical trial data. So I'll do either primary analyses of folks' outcomes, so looking at like say 2 to 4 time points. Doing secondary analysis of clinical trial data, similar number of time points, but maybe looking at mediators or even moderators of some type of growth process over time. My primary area of research is process research, so while other people are looking to see if treatments work, I look to see how treatments work, and I typically do that, yes, with mediators and moderators of self-report outcomes, but primarily, my primary area of research, I study the interactions between therapists and patients. And I essentially test the theoretical model that's proposed of a given behavioral treatment, and it's typically for substance use. So the longitudinal structure to the data is actually the session. We might divide the session up into quartiles. Typically, we're going to divide the session up into deciles, so it'll be 10 units of time. And we'll be looking at growth processes and decision making. So over the course of a session, is a client's motivation going up and their resistance going down? And if they were receiving a motivational interview, then that's what the theory would argue should be happening. So that's the type of stuff that I do. I think that's it for me. Let's talk about the objectives of the course. So we're going to talk about, we're going to learn the advantages of MLM relative to other approaches, so putting MLM in context of what we've learned thus far in terms of repeated measures ANOVA, regression, GEE. That's a lot of what we're going to talk about today. We'll understand the use of MLM for analyses where repeated observations are nested within individuals. So time points nested within people. As we heard, there are other types of nests, right? There's children in classrooms, there's siblings in families, couples, individuals in couples, folks living in neighborhoods, etc. This class, we focus on, a longitudinal time structure, individuals nested within time points. But the concepts are readily transferable. It has been my experience sitting in courses that I'm often listening to children nested within classrooms and making those translations. So this is the opposite. Examples would be randomized clinical trial data, EMA, daily diary data, experiments where you have, repeated exposures, and longitudinal survey data. So that was all mentioned. I think maybe not experiments, but other than that, I think that was all mentioned in your experience. So that's good. We'll do MLM in SAS and SPSS, so the syntax examples will be provided in both of those. We'll look at both time varying and invariant predictors of change. So an example is like, say, gender versus stress, right? So gender we think of typically as a time invariant predictor. Stress we can think of as a time invariant or time variant predictor. If we have a single measure of stress or some type of trait measure of stress or personality measure of stress, then it's not time varying. Versus if we're measuring stress over time, we're looking at it as a time varying predictor of some other either concurrently measured or lag measured type of outcomes. And that's what a lot of you guys are doing when you're doing the EMA studies. You're either looking at the stuff concurrently or with some type of temporal lag that you've essentially added to the data structure. We're going to build multi-level models, interpret the results, and write up the results for publication. So we'll talk about all of those things. This is a model building approach. So similar to structural equation modeling, you're essentially iteratively building a model and looking at, hopefully, increases in variance explained or increases in improvements in model fit by those additional levels of complexity that you're adding to the model. Of course, with some level of diminishing return. So essentially, you're finding that sweet spot where you've added, you've modeled your intercept, you've modeled your slope, you've added some of your predictors, you haven't gone crazy and made it unstable. You find that place, the right place in the middle. So those are the goals. In terms of what we're going to do today is an overview. We're going to talk about the course resources. We'll compare MLM to other methods. We'll talk briefly about the data setup and just doing the early descriptive work in exploring kind of what you think might be going on in terms of the change or the growth process that you're interested in. Next week is going to be basics and overview. It's basically focusing in on the level 1 and level 2 models from the equations perspective. In session 3, we'll start to build the models. So we'll start with unconditional means model, unconditional growth models, the composite multi-level model, and then the following week we'll move on to conditional models where we're adding in those covariates and looking to explain or to find a better fit to the data by addition of those predictors of substantive interest or those control variables that we think are important. In session 5, we do diagnostics, so looking at improvement over time or lack of improvement, and writing up results. And then in a final session, we'll do odds and ends. We'll do, I don't know what we're going to do, because usually I leave 6 open. But options are MLM in the program HLM, which does have some advantages, does have some conveniences in terms of what it gives you automatically versus what you would have to do by hand in SPSS or SAS. So if you're doing, I don't know, does anyone work in HLM in here? One small hand. Oh, and another hand. Another come see, come saw hand.
Well, I don't know where my software is.
I have, but I ended up not liking it very much because I wanted syntax.
Okay.
More.
Okay. All right. So I don't have a lot of experience with it either, but I have seen talks and had folks give talks on it, and it looked good to me. But Ron says no.
It's awkward to use.
Uh-huh.
It feels like a 1990s program.
Oh, like a
yeah.
Fine.
Or at least it used to. My
yeah. Okay. I thought yeah. All right. Well, I'm not going to argue why it's good because I don't actually know.
Yeah.
But
can I ask
so
a question sort of related?
Yeah.
Is there, I mean, maybe we'll get to this, but it seems like a lot of people are using M+. Would you not want to look at MLM and M+?
We could look at, I can add MLM, M plus syntax. Like when we get into, I'm not going to be running models in class, right? So I'm going to be talking about it conceptually and then walking you through like sort of annotated syntax. So we could add M plus, and I would, if I had a request and sort of a, if I had a large enough number of people interested in that, then I can add that information, certainly. So there's one.
Yeah. No, it would probably be good to do because Rich Jones is trying to build an M+ community within the psychiatry department as well. So, and we're actually making some efforts to figure out ways to get M+ software available to trainees.
To everyone.
Well, not in your life. I just don't think it's going to happen. But so I think it would be good to add M+.
Okay, so we'll do it in all three. We'll walk through the syntax examples in all 3 programs. And power consideration. So in session 6, chances are I'll have a guest speaker who might talk about one or both of those things, but we'll see. And I'll also, take requests and so forth.
Can I just make one other comment?
Yeah.
A lot of the, the time varying prediction is often in terms of a growth parameter as opposed to, so I actually work with a lot of data that's multiple time varying things nested within people, but the question is more what's the correlation, for lack of a better word, nested within people as opposed to one time varying predicting a growth parameter and another time varying. So I think having some examples of that, that other kind of model might be useful as well, because I think other people have described data that may be like that as well.
Uh-huh. So where the correlation...
So instead of
how's-
modeling a slope or more complex growth parameter over time, it's simply
An intercept.
variable A, variable B, yeah.
Yep, but concurrent, but basically
Yes.
an average correlation over concurrent
Yeah,
time
that's
points.
nested within people.
Got it. Okay. Okay, I think I can handle that. All right, so what are the course resources? Your motivation, the more you put out, the more you get in. You know that about taking stats workshops. So if you do have data, following along with the topic from week to week is a great idea. And then you can also bring your questions into class. You can also, like if you get like error messages or run into any questions in the in-between time, you certainly can email me and ask me. I'm more than happy to offer support if I have support to give. You need a working knowledge of regression and repeated measures ANOVA. Other resources are the course website, which has this PowerPoint slides for the course. It has a sort of set of weekly curated readings for the course. Pretty much everything's posted, although the PowerPoints will change slightly because the PowerPoints are from 2 years ago. But the course is pretty stable at this point as far as the content. The topics, notation, code, and some of the graph sources are from the Singer and Willett Applied Longitudinal Data Analysis website. So who has made use of that website, the Singer and Willett? Okay, so a few of you. So this is a great resource. It's a great resource. It's kind of hard to see, but it's a great resource because you've got the chapter topics along here, right? So investigating change over time, longitudinal data, multi-level model, et cetera, and then you have syntax for across all of these software packages that are provided. Syntax, data, output. And even I think like some PowerPoint slides and stuff. There's all sorts of good stuff in there. So we've got M+, MLWin, HLM, SAS, Data R, SPSS. Basically an exhaustive list. So that's just continuing down. We focus on chapters 1 through 6. So any questions on that? I think I would encourage you to check it out if you haven't been there already and see what's there and what's available. I certainly borrow heavily from that website in terms of the resources for this course. So MLM can be a little confusing because it has a whole bunch of names. And so I'm just going to kind of walk through those. Multi-level modeling suggests a minimum level, 2 levels of analysis, right? Rather than that single between-person fixed effects level analysis that we might be used to working with, we've got 2. And it's also referred to as hierarchical linear modeling because it's sort of in where it's suggesting a hierarchical structure to the data. It's also known as mixed effects modeling, and that suggests modeling a mixture of fixed and random effects. So not just that interest in the between-person or population average effects, which is fixed effects, but also that within-person effects, which are random effects. Random effects regression or random coefficients model, again, just thinking about an extension of the regression model where we've layered on random effects parameters and the capacity to look at within-person questions as well as between-person questions. Unbalanced repeated measures analyses, that suggests handling the handling of unbalanced groups for time. And so the good thing about that is that you can treat, in MLM, you can treat time as a categorical or continuous predictor, and you also have more flexibility with missing data. So it's really kind of two potential advantages. So if we've got a clinical trial and one person, you show up for every single time point and you're a great participant and I'm a bad participant and I show up sporadically, so I have missing data at time points, but I also am showing up late, so my 3-month outcome your 3-month outcome is my 4-month outcome, and so forth. And so those are 2 things that multi-level models can handle. So yay, MLM. Why do it? Most flexible approach to nested or clustered data. Like I said, nesting is observations within subjects. The problem, if we were to do this with OLS regression, is that OLS regression wouldn't know that there were dependencies in this data. So if we had 100 people and 4 time points, OLS regression would treat it as 400 independent observations, and that would be incorrect, right? There are 2 or more levels of analyses. Level 1 is the within subject level. Level 2 is the between or among subject level. The composite model examines systematic inter-individual differences that incorporates information about within individual differences. So that's typically what you're doing. You may be just interested in within-person differences, but typical multi-level models are going to incorporate both sources of information. So some key questions then in longitudinal design are going to be, do subjects change on average over time, and how? So is it a positive slope? Is it a negative slope? Is it a linear slope at all? Or is it potentially quadratic or an S-curve, which we won't do an S-curve? Number 2, do certain within subject predictors interact with time to predict change? So for example, daily stress predicting time to relapse. So is there potentially a more positive, the more stress you have, the more steeper or the more negative your slope would be in time to relapse, for example, of, say, to smoking. Do subjects in one group change on average over time more than subjects in another group? So now we've got, does treatment do better than control, right? So we just got a question of 2 intercepts. And when I'm doing these arm movements, I'm saying, say this is improvement, and this is time. And then this would be, here's intercept for control, here's intercept for treatment, right? So that's your first between-person question about intercepts. Do subjects in one group, this is number 4, do subjects in one group change over time more quickly or more slowly than another group? So say, is treatment versus control changing faster or slower? So now we've got a question of slope. We've got the 2 intercepts, and then is the control like this, but the treatment is like this. So we've got not only a higher starting place for the treatment group, but we also have a steeper rate of change than we do for the control group. And maybe the control group's doing this and going like that, which we see often. They might both be doing that. But the control group's probably doing it sooner. Do within subject predictors interact with between subject predictors to impact change over time? So something, say, like gender by stress interaction predicting relapse, predicting the, say, number of days used in the past month, something like that. So that's where you have a cross-level interaction, right? You've got a gender between person effect, and then stress measured as a time-varying predictor is a within-person effect, okay? The opportunities are quite interesting. Any questions so far? Okay. You'll find that I repeat myself and talk. I try to teach at a very basic level because that's how I learn. Okay, bottom line, it does all of these things. We've talked about them all. The one thing that I will add that we haven't talked about is that it can be modified to handle other distributional assumptions. So it can be generalized to handle count data, zero inflated data, etc. So that's another advantage or another level of flexibility that we can enjoy. All right, now I'm going to talk about between versus within person effects because it took me a really long time to feel comfortable with this. And I think the reason it took me a really long time is that when we come up learning regression, we are asking within person questions using between person tests. right? So when we've been taught our regression analyses, say we are comparing a treatment and control group, that's a fixed effects between person contrast. But the inference that we're making is a within person inference. We're interested in what would happen to person A if they were to receive treatment or if they were to receive control. So we're making that inference. We're making a within person inference from a between person's test. And the same could be said for like stress, like cross-sectional survey research where say you're measuring, this person has a high score on stress, this person has a low score on stress. But really, we're asking a question about how stress affects the individual, right? So I'm just going to go over them. Within person effects are the variability of a particular score within person. So this is essentially the average of the average within person change, right? So an example might be that we collected a score we collected data on ice cream desire for every person in the sample. And it was a 1 to 100, where 100 is very strong ice cream desire. And then we might be interested in what predicts the variability. And so one of the first things that we might use to predict that variability would be time. So we would have repeated observations of ice cream desire over the course of April to August, so 5-month increments of ice cream desire. So the within-person question is then, how does subject I's ice cream desire score change if measured monthly from April to August? The predictor is month, the outcome is desire, okay? That's our within-person question. Then we might add on, because we want to improve our model fit, we might add on a between-subject question. So, for example, between person effects examine differences between individuals based on their group membership or based on their score on some type of measure. So say we look at folks in the North versus the South. So we're actually have like a East Coast national survey. Or maybe we measure we take a genetic marker of like a sweet tooth genetic marker, which would also be a between-person effect. And so then we ask, regardless of time, do those in the South desire more ice cream than those in the North, or vice versa? Or do those scoring higher on the trait sweet tooth scale also score higher on the ice cream desire scale? Okay, so those are both two examples of between-subject questions that we've layered onto our data. And then we wanted to get fancier because we think that there actually might be potentially additive or synergistic effects between the within-person effect of time, this movement from spring to summer, and these between-subject characteristics of being in the North versus the South, or having this trait sweet tooth. So you can think that potentially in the North you've got a steeper slope for ice cream desire because in the South the temperature doesn't change as much as in the South. Similarly with the ice cream desire, trait sweet tooth might synergistically increase the desire that is due to temperature change, which we're using a proxy of a month for temperature change. Make sense? Okay. All right, so why do we like MLM compared to regression? I'm moving a little fast. I think I have a lot of content and I was a little late. So if I'm going too fast, just raise your hand. This is all foundation stuff, so I think you guys are like, yes, yes, I got it. So MLM handles repeated observations while modeling a non-independence covariance structure. So MLM in comparison to regression is also considering both those fixed effects and those random effects, where we think about regression as being a fixed effects analysis. Regression gives us one population answer for all individuals, right? That predicted regression slope. MLM also gives us explicit modeling of time-related processes and also complex modeling of time-related processes. So we look at linear quadratic change. We're able to do types of, like, say, event-type coding. So is your slope in stress more positive or negative post-quit date in a treatment, in a smoking study, something like that, right? So that's something where we're looking at slopes, we're looking at pre-post events, we're looking at a bunch of different aspects of time. And that's great, because that's the stuff we're interested in. Missing data are better accommodated. So MLM is a maximum likelihood or full information maximum likelihood approach. So it uses all available data points rather than, say, regression or repeated measures ANOVA, which is going to remove certain cases due to missing data. Okay. And even better with missing data than, say, a generalized estimating equations, where MLM will use all available data and GE at least needs a pair data points. Okay. Now, repeated measures ANOVA is better than regression for repeated measures data, because repeated measures ANOVA does allow you to look at aspects of time, and most importantly, it accounts for the correlation in repeated observations, right? So regression just doesn't even know. But in repeated measures ANOVA, the correlation between time points is what's called an exchangeable correlation structure. So essentially, it's assumed that time 1 and time 2 have a correlation that is equal in direction and magnitude as time 2 and time 3. Now, if you have, that might be fine, right? If you have, say, an experiment where you're doing, 10 exposures 2 minutes apart or 5 minutes apart, you don't necessarily expect those correlations to change over time. You may or may not, right? But if you have a RCT data and you've got a 3-month, a 6-month, a 12-month, and then a 24-month, then those correlations, those, say, drinking scores 3, 6, 12, 24, are not necessarily going to have equal correlations. And so then you, if you were working with a GE model, would change the way it's adjusted. If you're working with a multi-level model, you'll actually model that structure, right? So in repeated measures ANOVA and in generalized estimating equations, it's an adjustment. It's essentially a nuisance factor that is accommodated. So that's good, because you're at least accommodating it. But the difference with the MLM is that it's being modeled as something of potentially substantive interest, okay, as a random effect. Retains within individual information about change. Spacing for time can be unequal, which is different than repeated measures ANOVA. Treats time as a categorical predictor. Uses all available information. Complex modeling of time-related processes. So at that point, there's some repetition there, but any questions? Okay. Disadvantages. It's currently a univariate method, and that just means that it's a univariate outcome. So if you have multiple outcomes, then you have to switch over to, say, a structural equation model and have that, and allow for that measurement model of the outcome variable. That's what I just said. It's an iterative process, so you might want to kind of jump in and specify your multi-level model and be done. But really, ideally, what you're doing is you're building your model incrementally over time, and you're examining the changes in model fit at each subsequent step. And that takes more time. But you learn so much more about what's going on with the data. It requires more programming. It may be that a simpler approach like GE will suffice, right? It may be that a simpler approach like repeated measures ANOVA will suffice. And if so, then use them. I tend to use GE more often unless I need, unless I think that I need to focus more in on those within-person changes, that those modeling those random effects is really important, and that I can't just kind of fit a correlation structure on the data and say, no, the associations between time points are this, and that we're done. Right? Make sense? Okay. You need enough cases, and not just overall, but also within the nests, right? For someone like me who might be interested in therapist effects, if I'm working with randomized control trial data, I've got, you know, one therapist nest that has 2 patients in it, and one therapist nest that has 30, another therapist nest that has 25. That is not great for a multi-level model, right? You want at least, I don't know the rule of thumb, but you want at least, I think it's like at least 10 to 20 observations within nests, right? We talked about that. Okay, so questions. That was all foundation. Do you get it? Any questions? Okay, so now we have to start analyzing data in our minds. So, the first thing we're going to do is begin with standard descriptives to reveal, just to look at general patterns within the data. This is what we always do, right? We want to look at the distributional form. We always do that. We want to identify potential outliers. We always do that. And we also want to look at the potential structure, or the potential structure, I guess is the right word, for time, right? Are these, you know, how are these individual cases changing in this data set? Are they changing? Are they not changing? Are they changing in one way, 2 ways, completely random ways? You know, I think that when you looked at the descriptive data, it's particularly if it's like a random RCT data, like it's kind of horrifying, right? Because if it's like survey data, you're like, yay, everyone's different, and I get to explain them. But if it's like RCT data, and they're all like that, and you're just kind of like, what? Okay, but my treatment's supposed to be better than that, but never is. You have to get your data ready, so it's a different data structure. What are these 2 data structures? There is the person level data set, which is the one that from the regression tradition is what we're used to dealing with, right? So each person has 1 record or 1 row in the data set. So if you have ID 111 and they have 5 time points, it's T1, T2, T3, T4, T5, right? That's what, and then you've got 1, 1, 2, right? So you've got multiple rows, each person gets a row. That's also called a wide data set. It's also called an unstacked data set. It's the data set that you use when you're doing ANOVAs, when you're doing regression, when you're doing SEM. Yeah. There's also the person period data set. And there, each person has multiple records or multiple rows for those repeated observations. So this is also called a long data set or a stacked data set. So say, we're going to look at one in a second, but I like doing hand gestures. So say ID 111, and you've got 5 time points. You've got ID 111, ID 111, ID 111, and you've got T1, T2, T3, T4, T5, rather than T1, T2, T3, T4, T5, like that. MLM, GE are both going to want that type of data structure. So, this is an example. This is from the Singer and Willett website. So the National Youth Survey, and there's some delinquent youth, potentially delinquent, we don't know. We don't know if that's like, we don't know what that kid's drinking. But this one's looking out, so they're up to no good. So for this study, parents and youth were interviewed about events and behavior in the preceding year. So this is a longitudinal survey study. There's demographic data, socioeconomic status, disruptive events in the home, neighborhood problems, etc., deviance indicators, etc., etc. This is a NIMH longitudinal study. So, the variables that we're going to work with is simple, right? Subject ID, we need that. The time variable could be age and years. So in longitudinal study, when some of you are working with data on kids and their outcomes and some behavior over time. So chances are you're going to want to code your data as 12, 13, 14, 15, 16, like that. It could be follow-up time point. You might have that as T1, T2, T3. You might have that as 3, 6, 9, 12. You might have it measured completely continuously, so months 1 through 12, where you've got missing data points for individuals depending on where they showed up in their in the follow-up period. You have the outcome variable in a longitudinal data set, or so a long data set, a stacked data set. This is indicated by a single variable. So the example here is TOL, which is the score on tolerance for deviant behavior, and it's going to be measured at various ages. Okay? So are they becoming more or less tolerant over time as they get older? And then you have potentially other predictor variables. So it could be static predictor like male versus female. Exposure in this data set is score on the exposure to deviant behavior at age 11. So if you were exposed to some sort of riffraff at a potential age, does that make you more tolerant over time? Okay. So, let's see if I got a... Yeah, okay, so, where'd it go? Observations 1, 2, 3. These are their IDs, 9, 45, 268. This is their tolerance. This is the wide data set, so this is tolerance score age 11, 12, 13, 14, 15. Here's their whether or not they're male, so this is a female. We've got 2 males. Here's that score on the exposure, that continuous predictor, so we've got a categorical predictor and a continuous predictor. So that's what our wide data set's going to look like. When we flip it, we've got more observations, and the thing to note is that it's just because of the formatting of the slides that case 268 gets dropped from the picture. But you can see how ID 9 and how ID 45 correspond. So you've got your 5 time points, right? Age 11, 12, 13, 14, 15. The corresponding tolerance scores. So say tolerance at age 11 is here. Gets moved over here. Male, this is a female, so that just stays the same, right? Same with the exposure score stays the same, and then changes here, which is when we have the new subject. And that 45 should go down for 5 rows, and then we would move on to 268. Make sense? All right, so that's the difference. So here's the SAS code. Oh wait, get that page down. Okay. Here's the SAS code. So at the top we have the libname MLM seminar. This is where it's located. I've got it on my desktop. That is something that I don't know what it means. Does Ron know? It's something about how the data set can be shaped or something. Like how many words and stuff like that, or characters. Okay, so you name your data. You name your new data set. New person period data set. I can see that. New person period data set. But you're taking the old person level data set, so the old wide data set, and you're creating this one. You're going to array tolerance at 5 levels. So this is what it is. We remember this from the wide data set in the previous slide. Tolerance 11, 12, 13, 14, 15. We put in the do 1 to 5. Age 10 plus 1, so 11, or 10 plus I, sorry, 10 plus I. Tol, we're creating the tolerance variable, the long tolerance variable, which is made out of tolerance of I, 1 through 5. We need that output. And then this is just the keep statement, keeping those variables. Okay? SPSS, it's called the variables to cases command. you're going to make tall from tall 11, 12, 13, 14, 15. So you're going to make the new variable tall from these old variables. You're going to create an index variable that has 5 levels. You're going to keep, just like you did in the previous, ID, exposure, male, compute age, measure plus 10, compute time, age minus 11. So this is got centered at 11 so that your interpretation of your coefficients are starting at 11. If I'm working with SPSS, I usually do a point and click flip and then take that syntax and repeat with whatever manipulations, because it's a little bit easier, for me at least, depending on how many variables you have. It's like if you have a ton of variables versus if you just have 3 or 4, then it's just as easy to write out the syntax. So those are the 2 flip syntaxes. I think that these I pulled from the Singer and Willett website. So step 1 for this week would be to flip your data if it's not already flipped, okay? And come back and report on your progress. You're also going to, another thing to do this week would be to get just some descriptive sense of the sort of the nature of change or lack thereof in the data set. So, the main questions you're asking is there, is a linear fit for change the best fit? You might also notice that while a linear fit is probably the best fit, that there are a few different trajectories, and you might start thinking about, do I need to fit a different model for time, or can I potentially explain different different trajectories by a particular covariate, a particular predictor. But really you're trying to select the simplest model, and then iteratively look to explain or improve the model fit by adding in those predictors. So this is that same example. This is, but you've got more cases now. So this is like if you were to select, okay, I'm going to select 10 cases, and I want to look at their individual change in tolerance for deviant behavior over the ages of 11 to 15, right? So we have that case 9, we have case 45, there's 268, and then on down the line. So when we look at this, do we think that it's a linear change? What do we think? Like just looking at this, what do we think about the change in deviant behavior?
Probably linear, yeah.
Probably linear. Yeah, it seems to be close enough. There's a few flat ones. I think you would think, okay, linear is probably going to do it, and can I add predictors that might then separate sort of different types of linear slopes, or different levels. This is just another way to look at it. So these would all be, there's case 9, there's case 45. This is just a smoothed plot versus a non-smooth plot. It is linear, although not very linear, right? It's a very minimal slope, okay? But it looks like it'll work, right? So this is proc, SG plot, and SAS. I don't actually have it written down for what it is in SPSS. This is SG panel procedure. Proc SG panel.
Basically, you convert your SPS data to SAS and use those procedures in SAS. SPSS is not good at that kind of thing.
SPSS is not good at giving you visuals. Yes, I would agree with that. So we have 1 minute for questions. The assignment is
5 minutes fast.
Huh?
That's a few minutes fast.
So I wasn't late.
3 minutes for questions.
I wasn't late.
No.
I was like pushing
I'm
it. I was on the edge. I really actually thought that I left it in that. But anyway, okay. So, what should you do? You should go to the Google site and see what's there. There's already 3 readings there. You don't have to read them all. They're basically just 3 different introductory readings that I find useful. You could read them all. Think about what data you want to work with. If you already know, if it's not flipped, flip it. Email me if you run into trouble, and start running and give a go at one of those plots to start looking at the potential, at the individual slopes across people. Those are options of things that you could do. Questions?
So the way you just looked at, like, okay, what kind of fit do you predict from either an unconditional means model or an unconditional growth model here? The way you showed it here suggests that you do that visually. Is that how you wind up doing it, or do you evaluate fit statistics like you would in M+?
You would evaluate fit statistics. I do it visually just to kind of get a sense and have a plan. Although I would still be sort of confirming those decisions with the fit statistics. I mean, really, I think personally, I would just like hope for a linear slope. I mean, some of you aren't hoping for a linear slope because that's not the type of research you do. I mean, in this example, it wasn't really, there is actually not that much growth tolerance for deviant behavior, but perhaps when we stick in that experience of deviant behavior at age 11, maybe there will be a slope there and the other one will be flat. That's possible. Yes?
Yeah. There can also be significant variance on the growth parameter without there being a significant mean to the growth parameter, right? So everyone can change in a certain direction over time, but over the entire population there can be no change. So that doesn't necessarily mean that an unconditional mean describes the data well.
Right, and that's another thing that you're going to be looking at iteratively as you move along, is that unexplained variance within the person.
I think 2 things about what you asked. One is, it's always good to look at your data because none of us have enough neurons to really understand what the data really look like just from statistical output. The other thing is, when you look at your data and you get a sense, is it probably going to be linear? Is it going to be some really nasty function? It helps you prepare for how unpleasant the data analysis is going to be down the road.
Right. When things start going wrong, you're kind of like, oh yeah, but that's probably, yeah, exactly. And that's basically that's why we always do descriptive statistics beforehand. So we understand the nightmare that follows. Other questions? All right, well, my email is somewhere. It's not that hard to figure out, so if you have them, you can email me.
I could bring the email.